Folks, this is dim, and it has a gigantic mass. Furthermore, it's little. There are three indisputable pieces of evidence. Not too far off, embroiling a very monstrous dark opening in space can be terrifying. Contemplating the perils that prowl inside the immense span of space can be frightening. While this applies to the whole idea of space exploration, one part that has forever been captivating and frightening simultaneously is dark openings. These monsters of force have been the subject of endless examination. Scientists all over the globe have been attempting to sort out exactly what dark openings truly are and what lies inside them. However, all of that changes now. Neil deGrasse Tyson recently uncovered something immense. Our dark opening is less monstrous than the one in the center of the Andromeda Galaxy, our closest huge galaxy. So, we have dark opening jealousy? And I figure we do. Do we finally see what's inside a dark opening? Well, every last bit of it may just knock your socks off. Made from a huge blast, a dark opening's mass is gathered in a tiny district, making a gravitational force so extraordinary that nothing, not even light, can escape from it. Once something is in there, it will remain there until the end of time. These powers of energy come in different sizes, ranging from stellar dark openings, which can be a couple of times the mass of the Sun, to supermassive ones that exist at the centers of galaxies with millions or even billions of times the mass of our Sun. Researchers have noted the impacts of dark openings by implication for quite a long time. Each new piece of information uncovers more secrets. Even though they appear so enormous and strong that they can't possibly have a history, they do. There is no such thing as dark openings in space. They are made. They need the remnants of gigantic stars that have depleted their atomic fuel to be conceived. These stars go through a supernova blast, an astounding event marking the end of their lives. During a supernova, the external layers of the star are violently expelled into space, while the center undergoes gravitational collapse. If the center's mass is several times bigger than that of our Sun, the power of gravity overcomes all other forces, causing the center to fall inward. This collapse packs the mass into an astonishingly small volume, making an object with a gravitational field so strong that nothing can escape from its grip, thus creating a dark opening. The size of a dark opening is determined by its mass. Stellar dark openings, the most commonly known type, have a mass range from a couple to many times that of our Sun. At the center of a dark opening lies the singularity, a region of infinite density and curvature of spacetime. According to our current understanding of physics, the laws of nature break down here, and traditional theories cannot fully explain what occurs inside the singularity. In physics, a singularity refers to a point in spacetime where certain quantities become infinite or undefined. Singularities appear in theoretical contexts, such as at the beginning of an expanding universe, the supermassive singularity, and inside dark openings. As we concentrate on the Big Bang singularity, a key test emerges. General relativity, which governs gravity's behavior, breaks down as we move toward this initial state. Another theory, which seeks to unify general relativity with quantum mechanics, is needed to resolve this issue. Dark openings contain singularities at their centers, where the gravitational pull becomes infinitely strong. Matter and energy that fall into a dark opening reach the singularity and become infinitely compressed. This concept goes beyond our current understanding of physics. The challenge of singularities has led researchers to seek a theory of quantum gravity, which aims to bring together general relativity and quantum mechanics, offering insights into singularities and the universe's behavior. One approach to addressing singularities is loop quantum gravity. This theory proposes that at incredibly small scales, spacetime is quantized, meaning it consists of discrete, indivisible units. These units are interconnected loops or spin networks. According to this theory, the discrete nature of spacetime prevents infinite densities and shapes that create singularities in classical general relativity. As matter collapses toward the center of a dark opening, spacetime becomes increasingly small, preventing the matter from reaching an infinitely dense singularity. Rather, the imploding matter undergoes a quantum bounce near the center, where it rebounds and begins to expand. This leads to the formation of a new spacetime region inside the dark opening, sometimes referred to as a quantum dark opening. Stellar dark openings, the most commonly observed type, form through gravitational collapse at the end of a massive star's life. Once a star exhausts its atomic fuel, the outward pressure created by atomic reactions no longer counters gravity, causing the star to collapse under its own weight and form a stellar dark opening. Regardless of their mass, stellar dark openings have minuscule sizes, only a couple of kilometers in diameter, making them remarkably dense. The immense density of a stellar dark opening leads to the formation of an event horizon, a boundary beyond which nothing can escape. This event horizon marks the point of no return, where the gravitational pull is so strong that any object or information crossing it is captured for eternity. Intermediate mass dark openings have masses ranging from thousands to several million times that of the Sun, impacting their surroundings and cosmic evolution. Supermassive dark openings, often found at the center of galaxies, remain an area of active research. One theory suggests they evolve from smaller dark openings through accretion, where matter accumulates around a dark opening, converging over time to form a supermassive object. Charged dark openings, such as Reissner-Nordstrom and Kerr dark openings, represent extreme varieties. Reissner-Nordstrom dark openings are charged, but non-pivoting while bent. Dark openings are both charged and pivoting, presenting interesting peculiarities like edge halling. These sorts are for the most part hypothetical, as most dark openings are nonpartisan, coming up short on a net electric charge. With technology propelling researchers, we have noticed dark openings straightforwardly. In April 2019, the Event Horizon Telescope caught the principal picture of a supermassive dark opening in cosmic system M87, found 55 million light-years from Earth. Furthermore, gravitational wave observatories like LIGO and Virgo identified swells brought about by dark opening crashes, marking amazing leap forwards in affirming their presence. However, we're still attempting to completely comprehend dark openings. They are a reality, and proceeding to concentrate on them is vital for figuring out the universe's nature and behavior. Middle mass dark openings, while the exact mass range is still an area of ongoing research, are by and large remembered to have masses going from thousands to a huge number of times that of the Sun. These gigantic elements occupy the focal locales of most universes, including our own Milky Way. Their huge gravitational impact plays a pivotal role in shaping their cosmic environment and influences the development of systems. The arrangement of very gigantic dark openings remains one of the greatest mysteries in astronomy and is still not completely understood. However, a few hypotheses have been proposed to make sense of their beginnings. One conspicuous theory suggests that very huge dark openings develop from more modest dark openings through a cycle called accumulation. In this scenario, as matter, such as gas, dust, and stars, gathers around a dark opening, it structures a whirling disk known as an accretion disk. The enormous gravitational draw of the dark opening draws this material inward, making it spiral into the dark opening and merge with it over tremendous time frames. This consistent discharge of matter permits the dark opening to grow to a very huge scope. During the growth interaction, colossal measures of gravitational potential energy are released as the matter falls into the dark opening. This release of energy drives some of the most splendid and most powerful phenomena in the universe, including quasars and other dynamic cosmic cores. From these supermassive dark openings are charged dark openings, which represent a captivating variety in dark opening hypothesis. Charged dark openings are portrayed by the presence of an electric charge. There are two primary sorts of charged dark openings: Reissner-Nordstrom dark openings and Kerr dark openings. Each type shows particular properties based on the relationship between the dark opening's charge and other factors, such as rotation. Reissner-Nordstrom dark openings are charged but non-rotating, described by the Reissner-Nordstrom solution in general relativity. The charge of these dark openings influences their gravitational field. Despite this, they are fundamentally similar to uncharged dark openings. They have an event horizon, and the size of the event horizon depends on both the dark opening's mass and its electric charge. On the other hand, Kerr dark openings are both charged and rotating, presenting interesting peculiarities such as frame dragging, where the rotating dark opening twists the surrounding spacetime. These dark openings have both an outer horizon and an inner region considered the Cauchy horizon, a limit isolating the outside from the singularity inside. The presence of an electric charge in a dark opening presents a significant electrostatic challenge. Force notwithstanding, gravity influences the behavior of neighboring particles and matter. Charged particles, for example, might be repulsed by black holes. Electric charge modifies their directions, while charged black holes are hypothetically potential. They are not broadly expected to exist in nature. Most black holes are remembered to form from astrophysical cycles that result in neutral products, meaning they come with a net electric charge. If a black hole were to acquire an electric charge, it would almost certainly kill itself over time by attracting opposite charges from its surroundings. We've learned some significant things about black holes over the years, but in reality, seeing one makes a huge difference. We are familiar with these cryptic elements, and with technology progressing quickly, researchers have been able to observe and confirm the presence of black holes. Not only one, but two notable observations have provided direct proof of black holes. The first direct observation happened on April 10, 2019, when the Event Horizon Telescope collaboration captured a picture of the very large black hole at the center of the galaxy M87, found around 55 million light-years from Earth. The picture showed a glowing ring of hot gas surrounding a dark central area, representing the event horizon of the black hole. This observation confirmed the presence of supermassive black holes and provided phenomenal visual proof of a black hole's event horizon and surrounding accretion disk. Then, gravitational wave observatories like LIGO and Virgo made additional observations. They detected ripples in spacetime caused by the collision and merger of black holes. The detection of gravitational waves in 2015 was a great breakthrough in astronomy, providing indirect proof of black holes and confirming the existence of binary black hole systems where two black holes orbit each other before merging and producing strong gravitational wave signals. Black holes have long enthralled the imagination of both researchers and the public, inspiring various hypotheses and theories about their nature and role in the universe. Later advancements in observational technology have empowered scientists to explore black holes more deeply than ever before. For instance, the detection of gravitational waves from merging black holes has opened a new avenue in astronomy, allowing researchers to study these elusive objects through the waves they create in spacetime. The investigation of black holes also intersects with fundamental questions about the fabric of the universe. One significant area of research is the potential connection between black holes and dark matter. Dark matter, which makes up a critical part of the universe's mass, remains largely mysterious. Some theories suggest that primordial black holes, small black holes formed soon after the Big Bang, could account for some of this elusive dark matter. Moreover, the concept of black hole thermodynamics has emerged as a fascinating field of inquiry. According to this framework, black holes have entropy and temperature, suggesting they obey the laws of thermodynamics. The popular physicist Stephen Hawking proposed the idea that black holes could emit radiation, known as Hawking radiation, due to quantum effects near the event horizon. This radiation implies that black holes are not entirely black and can eventually dissipate over cosmic timescales, leading to intriguing implications about the ultimate fate of black holes and the information paradox. The information paradox itself raises significant questions about the nature of information in physics. When matter falls into a black hole, it appears to be lost forever, contradicting the principle that information cannot be destroyed. This paradox has prompted debates among physicists, with various theories proposed to resolve the situation, including ideas suggesting that information might be preserved in the radiation emitted by the black hole. In addition to their scientific significance, black holes have captured popular culture's imagination, appearing in countless movies, books, and artworks. Their depiction often leans toward the dramatic and mysterious, reflecting humanity's fascination with the unexplored world. Black holes serve as a powerful metaphor for incomprehensible forces and the limits of human understanding, challenging our perception of reality. Researchers continue to investigate the conditions surrounding black holes, especially the accretion disks formed by material spiraling in. These disks can produce extreme radiation across the electromagnetic spectrum, making them some of the brightest objects in the universe. Observations of quasars, which are powered by supermassive black holes at the centers of distant galaxies, provide valuable insights into cosmic evolution and the behavior of matter in extreme gravitational fields. Furthermore, black holes may play a role in the dynamics of galaxy formation and evolution. The interactions between black holes and their host galaxies can regulate star formation and influence the distribution of matter in the universe. The merging of galaxies, often accompanied by black hole interactions, can significantly reshape cosmic structures and contribute to the complex web of the universe. As researchers continue to unravel the mysteries of black holes, each discovery brings us closer to understanding the fundamental workings of the universe and our place within it.